Record. All right, we are live. So any of your questions will be preserved for posterity and posted on YouTube. I want you to know that. Let's see. I'll figure out where we're going here. Lecture notes. Let's see. Yeah, okay. So let's see, let's get back to where, okay, this is where I think we wound up. And I was writing this stuff on the board, but I can't really write it on the board because it needs to be on the screen. So, you know, this is in that packet I handed out to you. And we will go slow. So I think we started out, at the end of class rather, we wound up with this expression for enthalpy, okay? And again, we got a binary mixture. So it's dry air and water vapor. And so the I sub A is the enthalpy or the energy that's in the dry air. And the other term, the W is what pounds of water vapor per pound of dry air. And then IV is the enthalpy of the water vapor, so BTUs per pound. So when you multiply those together, you get the contribution for the moisture. And then this is the dry air, you add it together, and that's the total enthalpy. Well, okay, we're going to make it easier. So in Psych, we pick a reference, a zero reference for enthalpy at 0 degrees Fahrenheit and dry. Okay, so this enthalpy of the dry air, typically it's Cp delta T, right? Because that's an enthalpy change from thermo, Cp delta T. Well, this is Cp delta T, but we've selected the second T to be 0. And so if you're doing it in US units, it's 0 Fahrenheit is the reference. If you're doing it in degrees centigrade, 0 there is the reference. And so this is really a delta enthalpy, but the second temperature is selected to be 0, so you don't have to publish it. Okay. So this is how we're developing a nice little handy expression that can be programmed or something for enthalpy of moist air. And so this is how we'll do the contribution of the dry air. And then for the enthalpy of the water vapor, again, we pick a reference. The enthalpy of saturated water vapor is Ig at 0 Fahrenheit, okay? And then if we're not at 0 Fahrenheit, then we've got a Cp delta T, and this is the Cp for water vapor, which is 0.444 in US units that you'll see in just a second. So you can go to the steam tables and you can look up saturated water vapor at 0, or you know, the enthalpy of the water vapor at 0 Fahrenheit is 1062.1. And if you're doing metric units, you look it up at 0 degrees C, and it's 2501.3. Okay, so we're going to roll all this together into two handy-dandy expressions. And these are pretty, you know, these are pretty handy. You know, if you, I mean, you may be doing something senior design project or doing something later on. It's handy to remember that these types of expressions are out there. And these are good to within, you know, probably 2 or 3%, something like that, of, you know, if you went to the tables and got everything straight out of the tables. But so enthalpy of moist air is 0.24 T, and 0.24, that's the specific heat of dry air. That's Cp in US units, 0.24 BTUs per pound mass per degree Fahrenheit times the temperature in Fahrenheit. So that's all of the dry air contribution. And then this W, that's your humidity ratio. That's how much water vapor you have per pound of dry air. And then this bracket term is the enthalpy of the water vapor. So it works out to be, you know, pretty easy. And then in the metric equivalent is this expression where, you know, the constants change a little bit, but you're doing all the same thing. Okay? So you might have any questions about where that comes from? This, you know, extension, a little applied practical thermodynamics is all we got there. Okay, and so we've got a little example problem here. So we want to compute the enthalpy of saturated air at 60 and standard atmospheric pressure. So standard atmospheric pressure is what? 14.696. So I'm sorry, yeah. Is that right? Ah, I'm blanking it. Yeah, 696, isn't it? Yeah, because it rounds to 14.7.
Was the reference temperature always 0, or you can calculate?
Well, that's a really good question. Okay, and let me pull up this. All right, so these are dry air tables, the ideal gas property tables out of the back of your thermal book. Okay, so now this the temperature is degrees Rankine over here. So zero Fahrenheit is what? 460 or 459 and some change. So if you look here at 460, we get an enthalpy of 109.9 BTUs per pound. So see, this table has a reference, a zero reference at absolute zero. The Psych chart and this equation for enthalpy has a zero reference at 0 Fahrenheit. So, you know, so long as you stay all within the equation in the Psych chart, that's fine. But if you try to mix in numbers off of this, you have to adjust. Typically, you would adjust this number. And what you would do is you would simply take an enthalpy out of this table and subtract 109.9 from it, and that adjusts the reference to 0 Fahrenheit instead of absolute zero. And let's, since you asked, I was going to talk about it anyway. So let's do that. Let's look at the Psych chart. Here we go. Okay. And so, where's the only dry air on the Psych chart? It's the bottom. It's this bottom, this very bottom row down here. Oops. There we go. Okay. So let's pick a number. What did I pick a number? Let's pick 100 Fahrenheit, because that'll be easy to find in the other table. Okay. So here's the enthalpy scale. Down on the bottom, there's 25, there's 20, and this is BTUs per pound of dry air. Okay. So at 100, how would you read that? What would you read that to be right there? Where that 100, say you got those little kind of slanted marks. It's about 24, right? Because there's 25, 24, 23, 22, 21, 20. Okay. So off of the Psych chart, that enthalpy of dry air at 100 is, you know, I mean, it's not perfect, but it's pretty close. It's pretty darn close to 24 BTUs per pound. Okay. Well, so let's see. In Rankine, 100 Fahrenheit is what? It's going to be 460 plus 100, so it's going to be 560, right? Okay. So let's look at 560. 133.86. Okay, so if I take 133.86 and subtract off 109.9, I get a number I can compare to the Psych chart. I'm adjusting the reference, okay? So 133.86 minus 109.9 is 23.96. So it's just a smidgen under 24. So, you know, yes, you can use values out of this table if you needed to, along with values from a Psych chart, but you've got to adjust one, or you're going to get some pretty wrong answers if you don't adjust one for the reference. Okay, everybody good? I don't know that we have to do that much in the psych problems, but there's a possibility, you could go to work out there someplace and for some reason need to pull an enthalpy out of a table like this. And if you don't adjust it, you're going to get some pretty crazy numbers. It's going to be hard to explain to the boss man where that number came from. Okay. Not that one. Let's go back to this one. Okay. So they just put some, and it's really good as you study, prepare for the test, go back and study these examples. These examples in here are straightforward, but they're really pretty good at illustrating the use of the equations and the concepts. So let's see, compute enthalpy of saturated air at 60. So saturated air, relative humidity, 100%, okay? And standard atmospheric pressure. Okay, so this is our base, one of our basic equations, the only one we have right now to calculate a humidity ratio. And they just put the S on there because they said it's saturated. It doesn't have to be saturated, but in this problem, it is saturated because they said it was saturated. That's the only thing that made it saturated. Okay, so if it's saturated and 60, where can I go and get the vapor pressure for the water vapor? Can I find that easily? If it's saturated and I have a temperature, I can go to the steam tables. Okay, so let's see. There we go. I got this guy. Sometimes it won't let me go but one direction. I give y'all vertigo here or something. All right, so we're 60. We're getting there. Okay, so 60 out of this table, I think the table he used in the book doesn't have quite this many digits, but see, so there's your saturation pressure, 0.25635. So if that air is saturated at 60, that is the partial pressure of water vapor. End of story. If the relative humidity was 50%, it would be half of that, So, so some of this stuff you just got to memorize, but it's not hard. I mean, it couldn't be any easier as long as you got your table. If you ain't got your table, you're kind of up a creek without a paddle, but, we won't do that to you in here, okay? So that's where that saturation pressure comes out of. So 0.25, say 64, say 63.5, something like that. So if we go back, say 0.2563. Well, so that's the vapor pressure of the water vapor, and that's the piece of S, and it's an S instead of a V because it's saturated. And then the piece of A is just the total pressure minus the saturation pressure, okay? Because that's all we got left is dry air, okay? So you just plug the numbers, and it comes out 0.01104 pounds mass, then his V stands for water vapor per pound mass of dry air. And then if you want the enthalpy, then you just plug in. So, the 0.24 comes in the equation, the 60s, the Fahrenheit. There's your humidity ratio you just calculated, and there's your other 60, and turn the crank and you get 26.41. He says it's about 0.25% low, but shoot, for HVAC, that's plenty good. Okay, so let's look on the chart now. So remember those two numbers at 0.011 and 26.4. So let's go back here. Go back up. There we go. Okay, so we were 60 and saturated. So we're right here, okay? Because there's 100% relative humidity, and there's 60. Okay, so if we come across, we're a little bit above this line. So say that's 0.011 right there, if you read it right there. And we're just slightly above that. So see, it works. It does work. And the other was what was it, 26.4? So so now you got to kind of slide out here. There's 25, 26 is someplace in there. It's kind of hard to see on this, but yeah, so it's roughly 26 and some change right in there. There's 25 and there's 30. So yeah, I mean, the psych chart will work just fine. The key is the total pressure. If you look at this psych chart, what's it say? Sea level. So atmospheric pressure is 14.696 or 14.7. If you get way above or below that, you got to find a different chart. And they make a few. They make a high altitude. I don't know that they make a lower. I mean, it's hard to get much below sea level, you know, without being underwater or something. And this won't work underwater. Okay. Questions on that? Okay, so that's pretty good. Okay, so here's big topic. And actually, I have a video that's pretty good. And then I think we'll listen to the video just so you guys get to hear something else. And I can email the video out so I can stop the share here. So pause recording. Okay, so for those of you watching the video recording of the class, you should now watch the recorded video on adiabatic saturation, which we just watched in the class. Okay, so let's see. So now this is the same thing, so we can go through it really quick since you've already kind of seen the derivation. The only thing that changes here, the nomenclature is a little bit different in the textbook, but again, so phi is relative humidity, small t sub 1 is dry bulb temperature, this is pressure, which, you know, this is pretty much typically at atmospheric pressure, or usually pressure doesn't really come into the discussion very much. And there's your humidity ratio coming in. This is where we're adding the water, and this is the exit. And he uses this star to indicate that those states are at the adiabatic saturation temperature or the thermodynamic wet bulb. So here's the basic balance. Enthalpy of dry air at 1. There's the water vapor coming in at 1. This is the humidity ratio exiting. So that's pounds of water vapor per pound of dry air exiting, pounds of water vapor per pound of dry air coming in. So the difference is what was evaporated away per pound of dry air, and that's the enthalpy of the water. This is the saturated humidity ratio. That's the enthalpy of the vapor, the water vapor at state 2, and that's the enthalpy of the dry air. So then it's just substitution. What happens when you get this humidity ratio at 2, well, this is, see, these two are at, and this is messed up, but this is supposed to be the enthalpy of liquid water at the starred 2 condition. So they screwed that up in the printing of the book a little bit. But this is just, this is saturated vapor and this is saturated liquid. So that's the enthalpy of vaporization. So these two terms are by definition this. And so that's that middle term when you look at the enthalpy chart. It's usually tabulated for you. So there you have it. A very handy little relation to use. Notice this first term, what's the sign on this first term going to be? Is it going to be positive or negative? Got to be negative because T2 is less than, the largest it can be is 0. They could be equal if the air coming in is saturated. Then T1 and T2 will turn out to be the same thing. Other than that, if it's not saturated, T2 will be less than T1 because the wet bulb is almost always less than the dry bulb. So you see this first term here, when you're punching up, one time, I always check myself when I punch this up on a problem, make sure this first term is negative. Okay. And then this is, of course, the rest of the terms won't be. This is the enthalpy of vapor, etc. Okay. So what we typically do is we use this expression, you know, another expression for calculating W, to calculate the saturated W here. And it's easy because if we know this temperature, then we can look up this vapor pressure, because this is 100% relative humidity coming out. So you know the water vapor pressure is the saturation pressure at whatever the wet bulb temperature is. So, you know, I mean, you got to know the temperature coming out. So we use these two equations together a lot of times in actually calculating this W1. Okay, so let's do a quick example, and then I think that'll be about time to get out of here. So instead of doing this, let's make one up. We'll postulate the conditions in the room. I used to have a sling psychrometer and I could actually measure, but I don't have it anymore. But it feels pretty good in here. I'm gonna say it's 70 in here. So we'll say it's 70. Let's see, we'll call this the dry bulb. Okay. And let's say the relative humidity, let's do 35%. 35. So this will be percent relative humidity. Okay. So let's see, and total pressure, we'll just go with 14.696. Wow. I can type. Okay. All right, so let's see what we can do. Let's go back to not that one. Let's go back to this one, and we need to go. Okay, so let's see. Oh, well, let's see. No, let's add one more thing to this. I'm sorry. Let's say that we slung the sling psychrometer, and let's say that let's just pick a number. Instead of doing this, we would need to go to the psych chart and get the wet bulb, but to speed this up, let's say 55, sorry, wet bulb. Okay. So if we look at that equation, if I can remember it or not. This is hard. There we go. It's easy when you write it on the board, but it's not so easy up here doing this. All right, so let's say we're going to program this thing. So CPA is what, 0.24? Okay. And if we have a dry bulb and wet bulb, then this would be what, 55 minus 70 close. And this will be plus. Okay, so now we've got to get, we're going to have to come back to this. Now we've got to get this, the saturation humidity ratio at 55 degrees. So let's program that in here. And we're going to need, let's see, we're going to need that saturation pressure. Let me add a line or two here. I've never done this before like this. Okay, so we said at 55, it's 0.2141. So right here, so at 55, that's 0.2141. 0.2141. Okay. PSI. Okay. And we got total pressure. So then our saturation pressure is going to be equal to 0.6219 times this divided by the total pressure, this minus this. Okay, so everybody good with that? Do I understand that? Okay. Okay, so, and then we're going to need the enthalpy. Let's see. I know this is a little bit small over here. So we'll need this at 55. Okay, so it's the third one down. So that enthalpy of vaporization at 55 is 1062.14. That's saturated liquid, and that's saturated vapor, and the difference between the two is HFG or IFG. So 1062.14. So I'm going to need that. Let's stick it there. 62.4. Okay. Now, so we'll go back to this so I can see that equation. Okay, F2. And let's see, I think we better go back and put some, oh, you know what? I need an equal, don't I? There we go. Oops. Okay. Plus, so it's the W times this, close, and now we need two more enthalpies. Oh, don't give me that. What I just screwed up my parentheses. Yeah, that's okay. Okay, so now we got to go back here one more time. And so the enthalpy of the liquid is 23.07. 23.07. Uh-oh, that ain't good. Bless. 23.07. And the vapor, we got to look up the vapor at the higher temperature, which was 70. And so, okay, so there's saturated 70 is, so it's 1091.75 right there. 1091.75. F2. Yay, we're almost going to get it. Sure hope this is right. Whew. Okay, so we're saying that at, what we said, at 70 and 55, the humidity ratio in here should be 0.00, say 57 or 0.006. Okay, so we can check on the psych chart, see what it thinks. All right, so there's 70, and these are the wet bulb lines coming down like this. So actually 55 and 70 is right there, okay? Look at that. Just a tad less than 0.006. Whew, I was worried about that. Let's see, you read it right over here. Okay. So zero that, I'd say we pegged it. So anyway, that's what you can use this equation for. And it's really handy because you can buy an instrument that will measure wet bulb temperature easily. They make all kinds of stuff these days. So for like a building management system or something, you know, you can, if you want to calculate relative humidity, you can work your way through it, but you can get a sensor to just, you know, measure that wet bulb temperature, go into something like this, bingo. It lets you calculate properties. So, okay, I think that's pretty good. That might have run a little long, but I will get this posted for anybody not here, or if you can't sleep at night and you want to watch this again,